know is that f of a exists. Okay, there has to be an output for the input of a. All right, the second thing we want to know is that the limit as x approaches a of f of x exists. What that just means is that our left hand and our right hand limits at a, so coming from the left and coming from the right, agree. And then the third thing that has to be true is that f of a has to equal the limit as x approaches a of f of x. So you got to have a value for f of a. You got to have a limit that exists, and that value has to equal that limit. So let's look at some information here. I'm going to go ahead and fill this information out and come back and go over it with you. Okay, as you can see here, I found each of these values. You can go ahead and pause the video and take a look at these, and then go ahead and analyze at your own convenience. Questions are always welcome in class. Okay, so f is, if we use the definition of continuous in those three steps, right, what we want to do is we want to show why each of these scenarios show that f is not continuous at each of these points. So why is f not continuous at the point x equals -7? Well, that's a direct violation of the first rule that we've been looking for. F of -7 actually does not exist, so we can't even get past the first step. Okay, part B, f is not continuous at x equals 2. Part 1 is true, there is a value for f of 2. Part 2 is true, there is a limit as f approaches, or as x approaches 2, right? But those two are not equal, so it's a violation of the third part. F of 2 is not equal to the limit as x approaches 2 of f of x. Therefore, there's a gap in the graph, and it's not continuous at that point. F is not continuous at x equals 4, and this is a violation of rule number 2, and that is that the limit as x approaches 4 of f of x actually does not exist. Therefore, we got violation of rule number 2 there, and we can't move forward. Okay, so where is each of the following functions discontinuous and why? Use the definition. Okay, so if I were to rewrite this first function f of x and factor the numerator, what we'd see is that x is not continuous, f of x is not continuous at x equals 2 because f of 2 actually does not exist. So this is a violation of rule number 1. Okay, violation of rule number 1 on our list of requirements for continuity. And that would actually be a hole in the graph at x equals 2. Okay, part B is a really interesting question. This is a piecewise function. So for values where x is not equal to 0, it takes on this 1 over x squared shape. Okay, which looks like this. I'm going to actually make this red. The graph of this function when x doesn't equal 0 would look like this. Okay, and when x equals 0, we get this output value of 1. Okay, so clearly it's not continuous, but it does pass the first rule because f of 0 does actually exist. However, rule number 2 is where we have issues because the limit as x approaches 0 of f of x, if we look at both sides of this, would not exist. It does not exist because as we approach from the left and the right, they're not going to meet at any specific value. Therefore, we would have a violation of rule number 2. Not to mention, on rule number 3, this limit would not equal f of 0. So the limit f of 0 would not equal the limit of f of x as x approaches 0. Okay, the next example is very interesting as well. It's actually the same as our first example. The graph, what I'm going to do basically is I'm going to confirm rule number 1, f of 1 exists. Okay, so f of 2 exists. So f of 2 does exist. F of 2 equals 1, as we can see here. Okay, so rule number 1, check. Rule number 2, what I'm going to do is I'm going to take the limit as x approaches 2 of the function. Now I'm going to factor that function and go x minus 2 and x plus 1 over x minus 2. I'm going to go ahead and drop this. This is where the hole is. Right before it didn't exist, but now we have f of 2 equals 1. We want to see if this limit approaches that same value of 1. So as I do a direct substitution, I plug in. I'm going to plug in a 2 right here. Right? I'm going to plug this 2 in right here. And it looks like I'm going to get 3. So rule number 1 is okay, right? We've got a value, an output for f of 2. Rule number 2, we have a limit. It exists. However, in rule number 3, because f of 2 is not equal to, right, f of 2 is 1, and that's not equal to the limit as x approaches 2 of f of x, which was 3, then it is not continuous or discontinuous, non or discontinuous at x equals 2. Okay, our final portion of this problem is this floor function. Again, remember greatest integer function. And we went from 0 up to 1, and 1 up to 2, and 2 up to 3. Right, so this is 1, this is 2, this is 3. Okay, so for what values of x would this not be continuous? We could say that this would be discontinuous for x equal to any integer. Right, I think we can agree at 1, at 2, at what would end up being 3. The limits from either side would not agree. Right, so we have a limit and we have an output value, but those output values just don't equal those limits. Therefore, we would say for all integer values of x, for all integers, this function would be discontinuous. Alright, so let's look at right-hand and left-hand continuity, explaining why this function is discontinuous at x equals -1. So do I have an output for -1? And I will. I'll just check the endpoint of that interval. Alright, so I'll just plug in a -1 for x. So it looks like I get 0. Now coming from the left side of -1, all I'm going to do is input -1 here. Right, on the endpoint of that interval. And it looks like I get -2. Now the limit from the right side of -1 is what I did earlier, right? It's just plugging in a -1 here, plus 1, which equals 0. And because these two left and right-handed limits do not equal each other, right? 0 doesn't equal 2, therefore f of x is discontinuous. If I could spell discontinuous at x equals -1. Okay, so let's sketch it real quick, just to see what it looks like. Here is, let's graph this first part, x minus 1. Okay, so here is, although let's see the interval, it's going to be less than -1. So here would be a graph of this, but I only want it less than 1, right? And then it's x plus 1 for x greater than or equal to -1. So x plus 1 would go through this point, and greater than or equal to -1 for x. You can clearly see that, you know, a value exists for f of -1 there. However, the right-handed limit and the left-handed limit, they just don't agree. Okay, so just some detail work in the next part. A function f is continuous from the right at a number a if the value for f of a agrees with the limit of that value coming from the right on that function. Okay, and same thing on the left. If the output of the function agrees with the limit coming from the left, then again that f is continuous from the left. So if we go back to the integer function again, would this be right continuous or left continuous? Okay, so we consider closed and open and closed and open and closed and open. Okay, so coming from the right, it's continuous. Coming from the left, it's not continuous. All right, so we would say f, in this case, the integer function or floor function, is right continuous. So here I'm going to just write down some knowledge of what functions are always continuous, and you can study them on your own time. You can see everything that I wrote there: polynomials, lines, exponentials, logs, trig, and square roots. So with logs, you just have to be aware of the domain or any transformation going on. Same with the square root. And the trig is only going to be sine and cosine, which will be continuous everywhere. So another couple properties that you're going to want to be aware of are the composition of composite functions. So if g is continuous at a and f is continuous at g of a, then the following property works, right? Then I can take and find the limit as x goes to a of g of x and use that as an input for f. Likewise, if the limit as x goes to a of g of x equals L and f is continuous at L, then the following still works as well. So now we want to get into one of our big three. It's called the intermediate value theorem for continuous functions. It's a very important theorem. It's one of the big three, as I mentioned earlier. And we're going to talk about that here right now. Let's read the intermediate value theorem. A function y equals f of x that is continuous, that's important, on a closed interval a to b, takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c between a and b. All that means is that if I pick some x value c between a and b, then its output value right here must be between f of a and f of b. There must exist at least one value, f of c, such that it's between f of a and f of b. So let's use the intermediate value theorem here in a practical application. Use the intermediate value theorem to show that there is at least one root. What does that mean? That means that one value, one output, where y equals 0 of the given equation in the specified interval. Okay, so first of all, we know, and we have to show that it's continuous. And because f of x is a polynomial, we know it's continuous. Okay, so we got to check that off our list. It's continuous. Well, f of 0, if I plug in 0, I get 1. F of 1 is actually negative 1. Therefore, since f is continuous, I would write all this out, but I don't have enough space. And f of 0 equals 1, where f of 1 equals negative 1, there must exist some c such that f of c equals 0. This is the intermediate value theorem. Therefore, that f of c has to exist between f of 0 and f of 1. F of 0 is 1. F of 1 is negative 1. Therefore, c has to be between those two, and therefore that means that f of c should equal 0 somewhere. That's the intermediate value theorem.